Consider the following communication channel. A source transmits a string of binary symbols through a noisy communication channel. So I have a 0 and 1, and I transmit, and I have a probability of p and 1 minus p for transmitting 0 and 1. And I received incorrectly with probability of error 0 and error 1, epsilon 0 and epsilon 1 respectively. Errors in different symbols transmissions are independent. So I denote S as a source and R as a receiver. What is the probability of the symbol is correctly received? So part A. So I transmit 0 and I hope to get 0 from the receiver. And the no error is 1 minus epsilon naught. So the part A is I transmit correct, which means the probability of the receiver is 1, and also the source is 1, and the receiver is 0 and source is 0. And what is this mean? I receive 1 and the source is 1. That means I receive 1 condition on the source is 1 times I have sources 1 plus I receive 0 condition on the source is 0 times the source is 0. Because if I transmit 1, it still can possibly get 0, but I don't want this. So this 0 is only conditioned on I transmit 0. And this one is from the source is 1. So the answer is 1 minus epsilon 1 times 1 minus p plus the 0, 1. Part B, find the probability that receiving 1011 conditions on that 1011 was sent. So part B. One zero one one receiving and also 1011 sent. That means each time I receive the correct one. So it means the probability I receive 1 conditioned on the source is 1 3 times and 1 times for 0, then receive is also 0. For part C, in an effort to improve reliability, so each symbol is transmitted 3 times and the received string is decoded by majority rule. So in other words, a 0 is transmitted as 000 and it is decoded at the receiver as a 0. If and only if the received 3 symbol strings contains at least 2 zeros. What is the probability that the symbol is correctly decoded given that we send a 0? That means if we want to decode it 0, we will receive 001, 000, 001, 010, 100. At these two zeros. So if I decode as 0, that means I receive 000 or 001 or 010, 100. So the probability of this R equals this. Zero zero zero, 001, 010, 100. Depending on the source, depending on the source is 0. Is the probability of I receive 000. Condition on the source is 0. Plus the probability of I receive 001, condition on the source is 0, and the probability of 010, condition on the source is 0, and I receive 100, but the source is still 0. Then the answer is here. Part D. Suppose that the string of part C is used. What is the probability that a 0 was sent, conditioned on that the string 101 was received? Which is we have an error here. So it is the probability that the source is 0, but I received 101, which is incorrect. It should be 1, not 0. But this is the probability of I receive 101, but the source is 0 times the probability of the Bayes rule. And here's the probability of receive 101, which this we will use total probability law. What is total probability law? This I receive 101. It's from the probability I receive 101 from the source is 0, and the 101 the source is from 1. Then finally the answer is here, the total final answer. Last question. Suppose the string of part C is used, and given that a 0 was sent, for what value of epsilon naught is there an improvement in the probability of correct decoding? And assume that the error naught is not 0. So 0 was sent, and I still want to get 0 rather than 1. That means we want the probability I will receive 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, conditioned on the source is 0. This probability is greater than I just received 0 and the source is 0. We send 3 bits to make sure that we got the right 0 or 1 once we sent. So this is here. We can find the error is less than 1/2.